Hi there. Okay, we are going to begin our discussion on light, which is a little bit of a complex topic, but I hope to be able to concentrate on the areas of it that are most interesting and most informative. So the first thing that we're going to talk about, this is Unit 4, is all basically about light, how light operates, what it is, and how it interacts with materials, and how we use those for clever devices. So we begin our topic of light by discussing the wave nature of light. We want its wave properties. Okay, so we take a three-dimensional axis and we make a perturbation in, by that we mean we perturb or we disturb space in an electrical way. Now, one way to do this is very much like if you take a ball on the surface of water that's sitting there floating, a beach ball, and you pushed it up and down, then you would cause a disturbance in the water, and there would be a ripple effect of the waves around it. Well, if you move a charge up and down, the same type of thing occurs in what we call the electromagnetic field. So we move up and down a charge, and the resulting electric field of a single wave of light may look something like this. Now, there's no reason that it has to go in the z direction, but I've chosen the z direction for our particular wave of light that we're looking at. And you can see that there is an E field here because it's green, right? This E field is then described by these, at any given time, the strength of the E field is described by this graph. So at this point in time and in space, it happens to have this strength. And then it's pointed downward, and then it's stronger pointed downward and weaker pointed downward. And then it's weak pointed upward and stronger pointed upward. And it just keeps oscillating like that, just like the water wave that ripples out from a beach ball that's being pushed up and down on the water. Now, what we studied in Unit 3 about magnetic fields and about how they respond to electrical motion indicates that magnetic fields would also be formed because of the fact that there is a moving electric field, much like in the case of a charge that's moving or a current, right? So there is a magnetic field that's formed, and the interesting thing that occurs here is we have studied that if electric fields move, they create magnetic fields, and if magnetic fields move, then they cause electric fields to be disturbed. This is the result. Essentially, it's a little bit hard to see, but as I showed before, as the electric field rises in the positive direction along which that field is directed, then a lateral magnetic field forms to the side. And then as it bounces back and forth, then we get a lateral magnetic field backward as our electric field is pointed downward. This propagates the light wave in space in our z direction. So our electric field is in the y direction, the magnetic field is in the b direction, and the wave itself then is propagating in the z direction. Now, this is what we call the polarization of the light. The polarization is along the y direction because we indicate the polarization of a particular wave by its electric field vector. Okay, now you're not going to have to go into the mechanics of this particular electromagnetic diagram, all right? I wanted you to be aware of this because there's a really important piece of history that otherwise we would be missing out on. And that's that humans were trying to figure out for the longest time, if you bounce a ball in water, then, well, that's easy. We knew that as humans. You bounce a ball in water, you get waves through water, right? If you speak with your voice, then the waves move through air, no problem, right? So we always knew the waves you could transmit waves by providing a medium for them to travel through. The problem that we had was we didn't know how light got from the sun to the earth, and it was actually the development of electromagnetic theory that brought us to understand that light propagates through itself, essentially. It only propels itself. It does not require another medium, or if it does require a medium, we would call that the electromagnetic field. And so it's kind of interesting that this thing is sort of pushing itself through space. Okay, so or at least is rippling through space on its own with no medium required. So, okay, that means that it travels at the speed that all information is allowed to travel. It doesn't have any mass, so it's traveling at the speed of information. That means that it has a very specific speed, and that speed is given by the letter c, the speed of light. The speed of light is given as 2.997 times 10 to the 8 meters per second. Okay, so now that we've gotten this out of the way, I hope you have a visual for what we mean when we say light. We are from now on going to be referring to light in two different capacities. So we look at it as a piece of something that is flying through space, a packet of something that is flying through space, or we look at it as a wave that is propagating through space. And the reason that we can't settle on one or the other is because there was a long argument about whether it was a particle or whether it was a wave. And that it turns out that argument was never settled because it's neither one, but it certainly does have properties of both. And so sometimes we refer to it as a particle, and sometimes we refer to it as a wave. And this is what is known as the wave-particle duality. It is frequently stated that it is both a particle and a wave. I think that it is more correctly stated that it is neither, but we model it as one or the other. An example of how it's seen as a particle is that if you send a certain power of light, so a certain amount of energy of light, at certain metals, then electrons will pop off of the metal, and that's very interesting. But what's even more interesting is when Einstein studied how it pops off the metal, if he doubled the intensity of the light, then you would think that the electrons would pop off of the metal with double the veracity, or double the velocity, or double the kinetic energy, or something. But instead, they didn't. It doubled the number of electrons. They had the same energy, but they doubled the electrons. And then when he changed the color of the light, then it started changing the velocity with which the electrons popped off the metal. But it did not change the number of electrons that came off the metal. And so we realized that the light was striking the metal in packets, and that supported the particle approach to light. But we have long noticed that light can be bent, that it operates according to the same principles as waves. They're going through slits and diffracting. There's all kinds of other properties about light that support the wave model of light, so we can't really decide on one. Okay, so that's light. That is what light is. In the next video, our objective is to study waves in general and understand what a wavelength is, what a frequency is, and how those play into our mathematics.